All right, so I don't know yet whether or not I'm going to finish up section 3 today, but at the very least we'll start it and we'll finish most of it, if not all of it. And then we'll just talk about functions. So we'll finish our functions, and then if it takes us about an hour-ish or less to finish functions, then I'll go ahead and continue. But if it goes over an hour to talk about functions, then I'll go ahead and save countability and cardinalities until next time, and then we'll definitely finish with that. I don't think there's too much to cover on functions, but we'll see. So just as a reminder, right, we had a definition for relations, right? So we take, so for the following definitions, we'll just let A be a set. And in fact, we'll just let A and B be sets, right? So we had a definition that said the relation on A is a subset R of A cross A, right? And we recall that A cross A is the Cartesian product of A with itself, which means that we take all ordered pairs where the first element is from the first iterate and the second element is from the second iterate. So now we can also talk about a relation from a set to another set. So we can define a relation from A to B in exactly the way you think, right? This is the subset R in A cross B, right? And so the reason we're doing this is so far, all we've talked about is sets, right? Even though we've talked about relations, the new type of object, relation is still a type of set, just by how we define it, right? It's just we have a more narrow way of looking at it. Just like we can say, a square is a type of rectangle, but not the other way around, right? A relation is a type of set, but a set is not just a type of relation. So we are creating more mathematical objects in our vocabulary, but we're still living in a world that's talking about sets and only sets. So if we want to define a function, maybe we want to have a way to do it using sets. And that's why we talk about relations, right? Because when I have a function, I have two values. So let's look at a couple example functions, right? If we have a function, say f of x equals x squared, and it looks something like this, right? How would we talk about points on this function? Points on this function, right, for example, are ordered pairs, right? And these ordered pairs are exactly what you see in the relation. So for example, if you think of this function as an object, I can ask you, okay, is this object in the set? So if I pick a point up here, right, maybe 1/2, 1, I can ask, is 1/2, 1 in the set? Is it in the line that I'm drawing to represent this function? And the answer is no. Where do all our points come from? It comes from the xy plane, right? And the xy plane is just R2, right? I use a squared here. Some of you might not have seen this notation, but you might have seen R2 used to represent the xy plane. Well, what's the number squared? It's something times itself. But this idea of product or multiplying sets, we think about as the Cartesian product, right? So when we say R2, what we really mean is R cross Y. Right? So you can see our first coordinate should be from R. So second coordinate should be somewhere from R, right? That's where our XY plane comes from. So we can almost see that that is the type of relation we want to talk about, right? So a relation, maybe it is on A, right? Maybe it's all functions we talk about are from R to R. But that's not necessarily true. You've seen stuff like changing this one or change. So if I have a function, maybe we can talk about the domain or the range is our terms that you might have heard before that will formalize it a little bit. But those don't necessarily have to be all the real numbers, right? So how we change that is essentially changing this A and this B, right? So the idea is a function we can talk about as a type of relation. What's another thing you guys have learned about functions very briefly is, if I wanted to do something like a circle is not a function. Why? it fails the vertical line test. I can draw a vertical line that goes through multiple points. That's not allowed as a function, right? That's one of the things we say in like high school, even before that, is okay, a function, you know, you can draw it and you put a vertical line on it and it doesn't go through multiple points. Also, another thing is a function has to be defined on its domain, right? In other words, you know, if I say a function is from R to R, then I have to be able to evaluate at the domain, right? You guys have seen this before. You guys have probably answered questions like, oh, find the values of X for which this is not an X is not in the domain, or you can say find the domain of this, and you say the domain is all real numbers except for 0. Why is 0 not in the domain? It's because you can't evaluate this at 0. So that's some of the kind of things you see for functions and some of the kind of properties of functions. In terms of set, when we formalize functions, I just want you guys to think of it as, you know, don't think of it as something that's too complicated. It's really just, it's a machine. It takes an input and it gives you an output, right? That's all a function is. And all it means is if I give you a single input, it has to give me something else. It can't randomize what it gives out. If I give it something, it's always going to give that same thing back, right? That's kind of what the vertical line test is. If I have an X value here, there's no disambiguity on what it's going to give back, right? So for example, this would be a function, right? Because if I give you this value of X, it's always going to give me a single value of Y. It's always going to be the same thing coming back, right? So just think of it like a machine that, you know, you give it some input or inputs, doesn't matter. You can have functions of multiple variables. If you give it an input, it's going to give you the output, and the output is what we call well-defined, right? So again, I'll mention that in a little bit, but essentially, hold on, let me close the door. Sorry, there's some construction going on outside. But essentially, we all have these ideas of what functions are like and what properties functions have, but we want a way in which to formalize everything, right? This is kind of what we're talking about in this course is we'll find a way to mathematically formalize everything so that it has a proper definition, right? So let's list a few properties, right? So functions. What do we know? They have to be defined on a domain, right? And they also have to be, quote unquote, pass the vertical line test. Right, so how can we characterize these two things? So, first of all, when we note a function, the notation isn't just f, right? In other words, if I tell you a function, I need to also tell you what the domain and range are, or rather the domain and codomain are for what I want. So a function may be denoted f from A arrow B, where A and B are sets. Is a relation from A to B. And I guess there's two ways to say what I'm about to say. I'm going to write it this way. So we'll say that such that for every A in it, f of A has exactly one value. And maybe we have, and I like this because it's more obvious to see what these mean, but it's almost a bad definition because I haven't defined what f of A is, right? So I'm going to put these in parentheses because that's what I want you to think about when you have a function, right? For every A, this is exactly one value. It can't have 0 values because then it means it's not defined at that point in the domain. And it can't have multiple values because that's when it doesn't pass the vertical line test. So this condition encapsulates both of these at the same time. But like I said, we haven't technically defined f of a, right? So let's maybe have this in parentheses and talk about what a more proper definition might be, right? So keep in mind that f we define as a relation. And what are elements of the relation? The elements are ordered pairs from A cross B, right? So we'll say that, let's see, so we'll say that such that for every x comma y in f, and notice now I'm referring to ordered pairs as being elements of this function, because these are ordered pairs in a function which is a relation, right? And we'll say that for every x and y in f, right? Let's see. And sorry, I'm finding it hard to come up with a good definition for this without like going too far into the details. Okay, we'll do this such that for every x1, x2, so I'll pick 2 points, right? X1, x2. Now I'll just do the x1, y1, x2, y2. Right, so I'm going to pick 2 points, right, in the relation. If these two are the same, that implies that y1 equals y2. Right, so essentially, if these two are the same, these two have to be the same. That you can't get multiple outputs. So this is a more formal way of saying it using the language that we have so far, but it's really easy to think of it because you guys know what f is, right? So maybe if this is in parentheses, let's use notation, right? So we'll note that for every a in a, so rather let f be a function from a to b, right? And then we have that for every a in a, we say that if AB is an f of A is defined, right? Notice I use the definition, not and qual, right? So we'll define f of A as this element with this. And this exists, right? We know this exists because if A is in capital A, then it's in the domain. So there must be one value such as this, right? So this is a formal definition of a function, but really, at the end of the day, this whole formal definition just refers to these two properties, right? We're saying that it has to be defined in the domain and it has to parse the vertical line test, and that's all, right? Other than that, as long as you give me any domain and any codomain, that's fine. So I keep saying this word codomain. Let's define some of the things that we can talk about with regards to functions, right? Let's define these sets. So, in other words, if I write this, we see that this is the domain, and this is the codomain. Now, the codomain and the domain are, you don't have to think too much about it. That's what we assign as the sets, right? When I talk about this function, when I give you a function and I give you two sets it comes from, you don't have to think about, oh, is this included in there? Is it included in the codomain? Does it ever reach this point? You don't have to think about that. Because for now, the codomain is just what I write here. I can change what I write here and the function would still work, right? So let's not think about that for now. We'll get to a better definition of it. Some books define what range is here first. I don't like doing that. I prefer talking about image and pre-image first. So we'll use those first. And from now on, we're going to be using this notation, right? I'm going to use things like f of little a, f of this value of the domain, and we'll take that to be standard notation that you're all used to, right? But we should have at least made a note of it first. Okay, so let's define these. So if f is a function, right, and f maps. So how do we say this, right? In terms of English, right? We say f maps A to B, right? And oftentimes, if you want something like, oh, f of x equals f squared, you can also say something like f maps x to x squared. Notice I put an extra line here. This means maps to. So this means x maps to x squared. But notice I didn't quantify x here, right? And that's because when you write it in this way, you have to always have given the set form, right, the domain and codomain, before defining how it maps it, because I have to know where these x's come from and what I'm allowed to do with them. So this thing I wrote in orange here, this is just an aside. This is not, you can't substitute this in here. But if you want to be more specific or more explicit about what your function is, you can write it this way, right? This is the same thing as saying f of x equals x squared, right? That's the exact same thing. It maps x to x squared for every x in the domain, right? So anyway, if f is a function of f from A to B, we say A is the domain, right? And here we know that f has to be defined at every point in the domain, because in part of the definition, I say f of A has to have exactly one value, right? So maybe maybe this is one part I should probably add on to this, because all this says is that they're they pass a vertical line test. I haven't technically said that it's defined in the domain, so I can say here, and for every x in A, there exists, and maybe I can replace this another way with saying that there exists a unique y such that xy in f. That's another way I can say that, right? But that's just all to be very specific about what the domain is. So we say that A is the domain of f, and B is the codomain of f. And again, notice that all I did was I wrote down A and B, right? I haven't used the function to compute anything about these yet. I just said that, okay, here's the domain, here's the codomain. The codomain is where I'm allowing my function values to be, and the domain is just defining what the value is, right? So now that we know that, let's be a bit more specific. And talk about some other things where we do know like what exactly is allowed to be in the set. So we can talk about image, right? So let f be a function that maps A to B, right? And I'll start using this notation. I won't say let f be a function such that f colon A to B. I'll just use this. And that's pretty much understood to mean that f be a function that maps A to B, where A is the domain and B is the codomain, right? So I'll just say for any subset, called S, a subset of A, and I want it to be a subset of A because I want to be able to evaluate it. The image of S by F, right? And that's what really the image of the set, really by this specific function. And we'll denote this F of capital X is as follows. Or rather is defined as follows. Right? F of S is exactly equal to set of all f of A such that, right? So notice that if I give you a lowercase in here, right, and that lowercase is a variable from the domain, then that's just a number. It's equal to a number, right? It's not a set, it's a number. And we can say maybe numbers are sets, right? Then we go back to the whole thing, but you can think of it more as a number rather than as a set. Whereas here, it is a set. The image is always a set, right? There's a difference between saying this versus this, right? They almost mean the same thing because A is a point, a set containing one value that's also technically a point. But once this is a set, when I take the f of a set, now I'm taking the image of a set. This is not an image. This is just function evaluation, right? I'm evaluating function at this point. So maybe this is B, but then the answer to this would be the set containing B. And we've seen that these aren't the same thing, right? So remember that when I have f and I put something inside there, well, I don't mean the same thing. Depending on what's inside the argument, that changes our answer. If I'm saying f evaluated at just a point, that's just giving me back a number. But if I'm evaluating it at a set, I'm talking about the image, right? Similarly, we use the same function. And maybe I could have put this into the same definition, but that's neither here nor there. So for any subset, let's see, what's a good name for this? I'll say P in B, right? Notice now this is in the codomain, right? Now, just like we had an image, now we have a pre-image. The pre-image of P by little f, the function, and we'll denote this like so. And I'll come back to this in a little bit, is exactly what you would expect. It's the same thing, right? It's this, except flipped, right? So the pre-image is defined as all the values A such that f of A is in P. Right, so I'm taking all possible values where when I evaluated that, it's in this P, right? And so why do I use element instead of subset here? Is because this is a point in a set rather than a set contained in another set. So there's a distinction I want to make here. A lot of people confuse this for the inverse, right? It's not. Every set in the codomain has a pre-image. This pre-image could be the empty set. It could be all of the domain. Obviously, it has to be within the domain by definition, but it could be anything from the empty set to the entire domain. It might not even be defined, right? Inverses aren't always defined, and we'll get to that in a little bit, but note that this pre-image always exists. And so when we start by defining stuff, we'll define this as a pre-image, right? Not as an inverse. We use this notation that looks like an inverse, but imagine that you don't even know what the inverse means, right? Imagine you haven't even heard that term before, because again, remember that we're kind of trying to develop everything from the start. So since we're developing everything from the start, we don't have an idea of what an inverse function is. And since we don't know what an inverse function is, we'll just use this notation for now. Okay? So we have an image and a pre-image. So a couple more definitions. The range of a function, and we'll call this function f from A to B again, is exactly the set f of capital A, right? So the range is the image of the domain. So this is the image of the domain. And so a lot of books will introduce the range first. They'll say, okay, here's what domain is, here's what codomain is, and oh, you guys have heard the term range, let's introduce the term range, and then keep going. I think this is sort of backwards because, image talks about how you can relate the function to any subset of the domain. pre-image related to any subset of the codomain. That's easy to think about because now we can extend this up to a range, right? What does it mean when we're talking about the entire image of the entire domain, right? Because the domain, right, A is a subset of A, so that's part of this definition. So I think it almost makes more sense to have these definitions before we talk about those. But now we know what the range is, right? So back in like high school algebra or college algebra, when you guys talk about, okay, what's the range of this function? This is exactly what that means, right? What are the values that this function hits? If I have the function x squared, right, the range we say is 0 to infinity, but we almost say that just by inspection, right? That's what you're used to doing, right? But now we have a formal definition for how we would get that range. It's exactly the image of the domain, right? So we know the domain is all real numbers, right? What is the image of the set of all real numbers by this function, right? So that's what we're going to do here. Okay, so these are a lot of the terms that will formally define self-related functions. For those of you who have done a lot more function theory, and for those of you who are going a bit deeper into mathematics, here's another definition. A lot of you won't need this, or will never run into it again, but it is something that comes up. So the fiber of a point B in B for the same function, right, is denoted the pre-image of the set containing the point B, right? Because again, we don't have a, I can't, right now I can't say F inverse of B without the set brackets because there's no definition for that. I don't know what that means. There's no inverse function yet. So this is denoted like this, right? And it's exactly the pre-image of a point, right? So pre-image of a point is called fiber. I guess I'm using British spelling. Most American books, well, all American books will use the proper American spelling, but it's really just the fiber, right? The reason for this is sometimes you draw a function, the fiber is really just this line extending upwards, right? You can almost think like, okay, I have a function at a point, right? And then maybe I can see for other functions, I can look at all the other points associated with that value, right? So you'll see this fiber extending upwards. So a fiber is really just a pre-image at a single point. Okay. That's more for people who are going to like differential geometry, algebraic geometry, and stuff like that. Unless you're going pretty deep into algebraic geometry, algebraic topology, and stuff like that, you really won't see the term fiber pretty much at all, and you won't use it like ever. But for those of you who are, that's what that means. Okay. So now we have a lot about a lot about functions, but so far I've only been talking about a single function, right? We haven't tried to put them together because that's what we've and that's what we've seen a lot in previous classes. We generally know about function composition. So let's talk about function composition, right? So I'll write it as a definition, right? So if f be a function, and let me see how I want to do this. I'll say f is a function from B to C, and G is a function from A to B, where A, B, C are sets. Right? We define the composition of f and G. And I guess I'll say the composition of f with G in this order. Right? Generally, I can say this, but try to be clear about which direction the composition is. You can usually use the word after to tell you which direction it is. But I'll say the composition of f with G is defined as the function. And by the way, this isn't part of the definition, but what I'm about to write, you can prove that this is a function, right? So that's not, I'm not proving this here, I'm not proving that it is a function, but I claim that what I write will always be a function. right? So this, I claim that this is a function, right? And I say that such that for every x in A, this function evaluated at x is exactly defined as f of g of x. Colloquially, we'll usually say f after g. I don't know why more people don't say this, but like when people are first learning about composition of functions, they're always confused which one goes first. It's like you kind of have to read this from right to left. Like you do g first, then you do f. Because here I'll plug x into g first, and then plug it into f. I'm kind of reading right to left, right? The easiest way I always talk about this is when I write it this way, I don't have to think about which way it goes. I'll just read this in English as f after g, and when after tells me that it comes afterwards, right? This simplifies it like 1,000 times, and I don't know why more people don't do this when they teach it, but that's a really good way to keep it in mind. So essentially, I've just defined composition, right? So in other words, the thing is, I'm claiming that this is a function, right? I claim that this guy is a function that satisfies the definition that I gave you earlier, and maybe you guys can do that on your own time, but it also shouldn't be hard to see, right? The fact that it's a function comes from the fact that f and g are functions, right? So those are all defined. They're all, defined. They all pass the vertical line test. So this should be fine, right? And the idea is I start from point in A, G takes me from A to B. And now since F is defined on this domain, whatever I've had coming out, I can now map it to something in C. So that's a function, right? So this is function composition, right? So this basically just gives a proper definition for what you guys have seen already, right? And then you guys know how to do function composition. You take a value, you put it into the original function, you plug the form of that function into F, and you get a new function, right? And that's totally fine. Now, this is where you have to be careful. Is in high school or early college algebra, you get a lot of questions such as, what is the domain of the composition? And this is kind of an ill-formed question because they expect you to just put the functions together without doing anything else first and then talk about what the domain is. Well, that's incorrect because what did I do before doing composition? I defined my domain and codomain for each of f and g, and essentially the domain of f has to match up with the codomain of g. And sometimes when you're just putting random polynomials together, that won't always be the case. So you have to make sure that matches up first before you can talk about composition, right? I can have two random functions whose domain and codomain don't match up and talk about what this is, and it's perfectly fine, right? I can put them together and that, ask ourselves, okay, if this were a function, what's its domain and codomain? That's perfectly fine. But even though it looks like composition, that's not composition. Because we define composition as only what happens when we're putting things together who have the domain of one matching the codomain of the other, right? That's how we define composition, right? So again, this is why I stress definitions, because definitions give us a solid way to talk about whether we are looking at the right objects. What are we looking at the right things to put together? Because sometimes in math, people will colloquially use these terms to refer to something that's similar in idea, but not exactly it, right? So I can talk about maybe f of the square root of x, and f of x equals square root of x, and g of x is maybe like, I don't know, something that maps to negative numbers or something like that. And so I can talk about what happens when I put these into another, but that's not well defined because, for example, negative numbers would not be able to go into a square root function, right? So we want to be careful with stuff like that. Be careful about calling those compositions because they're not compositions. You're just using the idea of composition to put things into other functions, right? So that's composition. Well, the main reason why we want to talk about composition is I keep hinting to the idea of there being an inverse, right? Well, let's talk about that. We don't just want pretty images, sometimes we want proper inverses. And so before we even talk about inverses, let's see. Actually, you know what? Let's not talk about inverses yet. I'll leave that for later in the lecture. Let's take it aside and talk about different types of functions first. Now, once we talk about these different types of functions, then we can define an inverse. So so far we've been talking about functions as polynomials, right? The stuff you usually f of x equals x squared, square root of x, stuff like that, right? But let's avoid that for now. Let's talk about simpler looking functions because this will allow us to look at, some other ways to define things. Let's just look at finite sets, right? So we can draw these same Venn diagrams that we did before, right? And we can talk about ways to talk about a function. I can list a function by saying that, okay, there's a function f going from x to y, and I'll denote it by something like this, right? And so we can see that, okay, there's values here, and each of them get mapped to something in the codomain, right? But then there's all these properties where, oh, what is it a problem that we're missing these guys? Is it a problem that there's two guys going to the same guy over here, right? We have names for this. So I'll give you two definitions, and we can look at some examples or counterexamples of these guys, right? These are very important definitions in mathematics. Pretty much anytime you talk about functions, you want to know what these definitions are, basically better than the back of your hand, right? These come up a lot, and you have to know these definitions. Right. So we say a function f mapping from A to B is called injective, or you sometimes hear the term one-to-one. Both are fine, both are proper terms for it. So function is injective or one-to-one if for every x and y in A, we have that f of x equals f of y implies that x equals y. There are some books that will give this as the contrapositive, and they'll define. These are the same definition because those are the same statements, right? The contrapositive is the same as conditional. Some people would define this as what you see orange here. I prefer what I wrote down because this is typically easier to prove directly. The orange part says more about what the geometry of this looks like. In other words, what does it mean for a function to be injective? Well, here's the basic idea. And this isn't part of the definition, right? This is the definition, right? Injective just means passes the horizontal line test. That's all it means. In other words, if I draw a function out somehow, I don't want to, I should be able to draw a horizontal line, right? And it should only pass through one point. So for example, for a function like x squared is not injective because I can draw a line like this, right? I have two values that map to the same thing. That's what it means to fail the horizontal line test. It means I have two values in the domain that map to the same value in the codomain. I don't want that, right? So that's why you have this thing, right? This thing in orange essentially says, okay, if I have 2 points, right, that I'm plugging in that are different, and I map them up, their images shouldn't coincide. I should get different things. So what I just wrote here is exactly the horizontal line test in terms of like seeing it in action, right? So the orange is easier for looking at it. But in terms of actually proving it, right, if you ask to prove that a function is injective, it's typically much easier to start with what I wrote in white. So that's why I provided this is the definition, right? It'll be much easier to follow the definition than to use this as a definition. And every time I ask you to prove something, you say, okay, we'll prove this by contrapositive. We'll prove this by contrapositive every single time, right? We'll want to avoid that. So some people use this as a definition instead. But you can see it doesn't matter. It's the same statement, right? So for now, I want you guys to use this as the definition. F of x equals f of y implies x equals y, right? So for example, let's look at the line. And so by the way, I realized what I said was a bit confusing. What I meant when I said that we'll talk about like finite sets is it's easy to draw Venn diagrams like the one I drew before for finite sets, but then we can use this as an example to talk about infinite sets. So for now, right, if I have something that looks like this, 1-to-1 almost means one mapped to one and so on and so forth, right? So something like this is not injective because I have two things mapping to the same guy, right? This is not injective. If I remove this, you can all say, okay, what if I want the other thing? A lot of people get confused here. This is not a function. Why is it not a function? Because I have one thing mapping to two different things. That fails the vertical line test. This is just a relation. I can call this a relation, right? But not all relations are functions. This is just a relation. It's not even a function. So that's not even allowed, right? So we want something that looks like this, right? Where no two things go to the same object. I can even add things in here, right? That's still injected. Even though I added holes in Y that don't get mapped through from X, that's still injected. So now you might ask, okay, what about these holes? What if I don't want to have those holes? That leads us to the next definition, right? When we say a function is surjective or onto is another word people use for this. If for every little b in B, there exists an A in A such that f of A equals B. All right, so this is the definition of surjectivity. It means that if I pick any element in the codomain, there's always something that goes to it. So, if I again draw some B diagrams, and I want some sort of function here. This function is neither injective nor surjective. It's not injective because I've got two things going to the same guy. It's not surjective simply because there's a hole here. So you can see surjective just means there's a hole in the codomain somewhere, right? There's a codomain that doesn't have anything. What's another way to characterize this, right? Surjective means there exists a set that's a subset of the codomain such that the pre-image of that set is empty. It's the empty set. That's another way to talk about surjectivity, right? Pretty much no one uses this. I kind of just came up with this on the spot just because it's something that's easier to see, right? There's some empty hole. Nothing gets mapped to this. It has no pre-image, right? Well, it's really easy to make this surjective. Get rid of that, right? Because the only thing that prevents it from being surjective is there's some set whose pre-image is empty. So take away that set, I still have a subset, right? I'm essentially restricting the codomain until I have something that is totally fine, right? There's no subset whose pre-image is empty, right? And then if I want to make this injective, well, I just have to get rid of one of these lines, right? So maybe I can restrict the domain to make it, right? So now it's injective. So there almost seems to be sort of this nice connection once we have both injectivity and surjectivity, right? So if a function is both injective and surjective, or rather if it's both one-to-one and off-to, we say f is bijective, right? Other terminology, this is almost like an adjective, right? We use the terms injective, surjective, bijective to describe f. So going back to the whole this is an English kind of thing, right? We can use adjective forms, but we can also say things like f is an injection, right? We want to refer to it as a noun, would use injection, surjection, bijection. Right? Those mean exactly the same thing. It's just whether or not you're using it as a noun or an adjective. Right? I usually use it as an adjective, right? I'll say f is bijective or injective, but sometimes it is better to treat it as an object. F is an object. This object is a bijection or it's an injection or something like that. Right? Those mean the exact same thing. Right? So just if you ever hear that, note that this is not a different definition. It's just adjective versus noun sort of thing. So it almost seems like bijections have this nice property where it's just, if I have a thing here, it goes to a thing here, there's nothing extra, right? And in a finite case, you will see that this gives us a really nice thing. In a finite case, there's exactly as many things here as there are here, right? Well, let's formalize that a little bit. By talking about something called the pigeonhole principle. And the pigeonhole principle is really stupid. It really says, if I have more pigeons than pigeonholes, then at least one of these holes, right? At least one of these pigeonholes must house two or more pigeons, or rather, more than one pigeon. And it sounds really stupid to say, right? Because it's obvious. If I have too many things that I'm trying to fit into a smaller number of boxes, one of the boxes has to have one or two things, right? A lot of people call this the pigeonhole principle. You'll also hear this called the elevator principle, because sometimes you can think about it as like, okay, if there's 10 floors in a building and I have 20 people in the elevator, there must be at least one floor where more than one person gets out, right? So these kinds of ideas talk about kind of injectivity, right? So let's kind of draw a picture of this. If I have more pigeons, right? In other words, more things in my domain than I have things in my codomain, there's no way to make this injective, because I can try to make it as injective as possible, but now part of the definition of a function is that I have to map everything into the domain. This has to go somewhere. No matter what I choose, I have to break injectivity, right? So what does this mean? This means that we can compare the size of these finite sets, right? So now, I know I kind of moved from A to B to X to Y. Sorry about that. I probably should have been more consistent, but let's not worry about that. It should mean the same thing, right? So let F be a function of X to Y. If X is greater than Y, F cannot be injective. That's what the pigeonhole principle says, right? But then let's look at another thing. If X is strictly less than Y, well, let's draw what happens, right? If this is my X, and this is my Y, I can make this as nice as possible, right? But there's always going to be one thing in Y that's left out, right? There's always going to be one thing that I can't map to because I can't fill the vertical line test with the other part of the definition of a function. And in this case, F cannot be surjective. Right, so you can see these two statements are true just from the pictures, right? And this really comes from the pigeonhole principle. What does this give us? Let's take the contrapositives of these two statements. What does the contrapositive say? If F is injective, right, the opposite of this, what's the opposite of that? We have that. And so similarly, if F is surjective, right, then cardinality of X is greater than or equal to the cardinality of Y, the opposite, right? So you can almost see what happens when you put these together, because these are just numbers, right? What happens when I put those things together? Injective and surjective means bijective. Right? But wait, what does it mean if two numbers are both less than or equal to and greater than or equal to each other? It means they're the same. So this isn't the definition. We just kind of figured this out, right? By the Pictionable principle, if we're looking at a finite set, right? Because if we're dealing with strictly greater and strictly less, then we have to be talking about most. We're just sticking with x and y being finite, right? Let's say their cardinalities must be a finite value. If that's the case, injectivity and surjectivity together give us that their cardinalities must be equal. This is going to change when we start talking about infinite sets, right? Because now we're going to use these, right? These just come from the Pigeonhole principle. We're going to use these ideas and apply them to defining these cardinalities for infinity, right? Because when we have infinities, maybe we'll see eventually why we can't just say this, right? Of course, 5 is less than infinity. Of course, infinity is greater than 7, but is infinity less than or equal to infinity? Well, it depends, right? If you treat infinity as just the concept singularly, then sure, right? Infinity is equal to infinity. But that depends on there not being multiple types of infinity, which there are, and we'll talk about that in a little bit. So before we dive into that, I just wanted to give you this. I'll keep that up there because it will come in useful. But really, when we talk about functions being injective and surjective, this idea of limiting to a finite case eventually will let us extend this to how we talk about cardinalities of sets for infinite cases, right? But these ideas of injectivity and surjectivity hold even for functions whose cardinalities are infinite. So let's look at an example, right? So I'll get rid of this because now we don't need this anymore. All we need is this guy. Right? I'm going to start with this function. So let f map from R to R, where f maps x to x squared. Right? This is the same thing as saying f of x equals x squared. This is I'm asking, is this a function? Right? Well, first of all, it is. Right? We know it's a function. Okay. Then let's ask if it's injective, right? And the first thing is, if we draw it out, we can immediately see that it's not injective, right? Because it fails the horizontal line test. And the question is, how do we prove this? So remember, the definition of injective is for all x and y, we have this implication, right? Well, that means that when we negate that, how must we negate it? So let me write it out again. Injective vaguely means that for all x and y in the domain, I have f of x equals f of y implies x equals y. That's the definition of injective. So how do I prove that's wrong? I have to flip this quantifier and then negate this statement. But remember that the negation of this is logically equivalent to P and not Q, right? So in other words, what this means is the answer is no. So to show it's not injective, we have to disprove injectivity, and so we prove the negation. So the negation is we want to show there exists x and y in the domain, which in this case is R, real numbers, such that P and not Q. That's the negation of this, right? What's P? P is the statement that f of x equals f of y. And not Q, x not equal to y, right? So how do we prove this? Pick an x and y that work, right? Well, let's just look at our graph and we can easily pick something. The x equals -1 and y equals -1. Sorry, +1. Right? Indeed, we have x not equal to y, right? Because 1 is not equal to -1. And also, we have f of x is equal to -1 squared, which is equal to 1, which is also equal to 1 squared, which is exactly f of y. Right? So we have that f of x equals f of y. So we've proven that this is not injective. Right? So remember that when we want to disprove something, it's the same as proving another statement. You just have to take the negation first. Right? Okay, so now we can ask, is this surjective? Well, again, I'll put it down here. Maybe surjective, the definition is there exists, right, for all elements of the codomain, there exists an element such that f of a equals b. Right. So what's the negation of that? Well, when we negate it, we flip the quantifiers, so there exists a b in the codomain such that for all elements of the domain, f of a is not equal to b. Right? So let's prove that this thing isn't surjective, because we can see that if it maps to all row numbers, I'm missing the row numbers down here. I'm missing the negative numbers. Right? So the claim is that f is not surjective. Right? In other words, by that negation, we want to show that there exists a b in the row numbers such that for all elements of the domain, which is also the row numbers, f of a is not equal to b. Right? So first, let's pick one, right? By looking at the picture, we have proof, right? We want to pick one that looks like it's makes it break from the picture. So pick a negative number, right? So pick b equals -1, which is a row number. Right? Now we want to show that for all a, f of a is not equal to b. But note that for all a in R, f of a, right, is exactly equal to a squared, which is always greater than or equal to 0, right? But for all values of a, this means that, so I'll just say this, thus, and again, maybe, so we can see this is a kind of a separate statement on its own, right? So now we can say let a be any arbitrary real number, right? F of a greater than 0 implies that f of a is strictly greater than b, because b is negative. But that implies since it's strictly greater, they can't be equal. Right? So I've proven my negation. And so I've shown that this is not surjective. Okay? So taking a look at this, and we said that, okay, this function is not surjective. Now my next question is, how do we force it to be surjective? Or how do we force it to be injective? Let's start with the easy one, surjective. What are the things that make this fail to be surjective? Those guys, right? So what if I change this function and I want to change its domain and codomain? So now I say that make this all the positive from that. And I'll just say R plus, that's all positive row numbers. I'll make this include 0, but it turns out it doesn't matter whether it includes 0 or not. So just for convenience, it's just strictly positive row numbers. If I look at strictly positive row numbers, this is fine, right? This is surjective, because now I don't get this problem anymore. Again, I still fail the horizontal line test. That's easy. Just get rid of the extras. Now I can't fail the horizontal line test. So make this R plus to R plus. Keep the same thing. So now I claim that this is both injective and surjective, right? And now it's pretty easy to prove that it's both injective and surjective. To prove surjection, it's easy. You pick an arbitrary point in R plus, right? Pick an arbitrary strictly positive row number, Can you find an A that works? Well, take the square root. Now that it's positive, I can always take a square root, right? And the square root always exists. The square root of a positive number is positive. That's in the domain, so this works. Therefore, this is surjective. For injectivity, now I no longer have this problem. So if I pick any two numbers in the domain, pick any two strictly positive real numbers, right, and map them to the same thing, well, f of x equals f of y tells me that x squared equals y squared. But then these are positive. When I take the square roots, I no longer have to worry about getting the negatives. I just have to take the positives because that's my domain. So now x squared equals y squared gives us x equals y. So this is injective, right? So it's very easy to prove that this is injective. Let's see one more example of proving a function is injective. I'll pick a pretty easy function and I'll give you some more complicated ones in the homework. But you kind of see, you'll start seeing this general idea, right? I'll give you one for injectivity and one for surjectivity, right? So f of x equals 2x, f mapping. So maybe I'll say f maps R to R, right? So this is my function. I want to prove that this is bijective, which by definition means prove that it is injective and prove that it is surjective, right? So what does it mean to prove that it's injective? So prove f is injective. Well, this means I respond to my quantifiers. My first quantifier is a for all. So I say, let x and y be in the domain. The domain is R. Perfect. I'll write this. Right? Then I want to prove this statement. In other words, suppose this is true, then this other thing must be true. Right? So suppose f of x equals f of y. Right? What is f of x? This implies that 2x equals 2y. But we're working with the real numbers, so we can really just cancel out 2 on each side, say 2x equals 2y, but equals, then x equals y. And I'm done. That's really all I have to do. I've proven that x is equal to y. That's my final goal. That's really what a proof of injectivity looks like. If I want to prove it's surjective, well, it's the same as picking one, right? So again, I respond to my first quantifier, let b be a real number, right? I want to show that there is a real number a. I say let a equal something. Again, I'll use this technique where I don't know what this is, but I know this is a real number, and I'll work backwards. Because at the end of the day, I want f of a equals b. Notice I'm doing the same trick I've shown you guys before, where I start at the beginning and then I start at the end and I'll work in between, right? Well, if I want f of a to be equal to b, what's f of a? That's 2a. Right? But essentially, I want to know what a is, right? Well, we're working the real numbers. So we'll imagine that we know all the properties of the real numbers that we use for so long, right? So this tells me that, oh, I just need this. If b is the real number, then b divided by 2 is also a real number, right? So if I start with that, I'll eventually get to f of a equals b. So I've proven surjectivity, right? And so this function is bijective, right? These are the typical ways in which you'll see injectivity and surjectivity proven. For injectivity, you start with two arbitrary numbers or values from the domain. You assume this thing, and you want to show that this is true. You assume that f of x equals f of y, and you want to show by a series of implications that x equals y. Whereas with surjectivity, we have two quantifiers, so we'll respond to both of them. We'll start by picking an arbitrary value in the codomain, then we'll pick a value that exists. Well, we might have to work backwards to see what that is, but essentially, what surjectivity is you give me a value in the codomain. To prove it's surjective, I have to always give you or be able to give you a value in the domain that maps back to the value you gave, right? So that's surjectivity, and that's how you prove it. You exactly construct that value for me, right? That's really all there is there. Okay. So I'm gonna try to finish up this section because I think we have enough time. That's the main idea of injectivity and surjectivity, which leads on to bijectivity. I'm going to spend a little bit more time talking about I'll just spend maybe a couple minutes talking about inverse functions, but then we can go on. One more thing I want to point out that some people in the past have asked me like, oh, why do we care about pigeonhole principle? Is it just to have this sort of injectivity thing? Well, the pigeonhole principle is kind of a rewrite of the definition of injectivity, but it also kind of gives us a way to talk about what's it called? To talk about non-constructive proofs. The example I always give people is, whenever I want to answer the question, are there two Texans who have the same number of hairs on their head? Like that sounds like a really dumb question, but the idea is, you can look it up, right? You can look it up in terms of like, you as a human, like just human limits, there's at most 1 million hairs of strands of hair on your head. You can't get more than that. But we know that the population of Texas is more than 1 million, obviously, right? So because there are more Texans than there are possible numbers of hairs on your head, there must be two of them that have the same number of hairs on your head. Anything else is impossible, right? And that's a non-constructive proof. I didn't pick out two Texans and showed you and counted the same number of hairs, right? If I wanted to, maybe if I made zero a proper number, then I can say, okay, pick two bald people that have the same number of hairs, it's zero. But if you want it to be positive, well, that's a lot harder. I would have to do that by a non-constructive proof, and the pigeonhole principle is one example of how we can do that. Okay, so the last thing of the function to talk about is inverses. First of all, we can talk about an identity, right? So for example, you're familiar with f of x equals x is the identity. In other words, an identity function is one that maps everything to itself, right? So identity function labeled usually ID on some sets A, right? So again, let A be a set. So then we have an identity function on the set mapping from A to A, such that f of A is equal to A, right? That's really what the identity function is. Okay, so now let's say that this gives us a way to talk about inverse functions. But before that, we'll talk about an inverse relation. Because remember, inverse functions might not always exist. But we have inverse relations, right, no matter what. So I can define an inverse relation R of a relation R from A to B is a relation from B to A, obviously, right? I'm flipping my domain and codomain, right? From A to B, from B to A, such that this is exactly all order pairs y comma x, such that x comma y is an R. Right? This is how I'm going to define an inverse relation. I start with a relation from A to B, and the inverse relation is one where I just flip everything, right? And this is similar to what you guys have seen for, at the very first thing when you guys first talked about functions, and you first talk about inverse functions, one of the first quote unquote definitions they give you in like high school is, oh, just flip all your values, right? Flip your y and your x. Well, the problem is that doesn't always give a function, right? That's why when they say flip everything, we have to talk about it as relations first. Because relations are just ordered pairs. They're just a subset of the Cartesian product. I don't care about this whole well-definers. I don't care about the whole, vertical line testing. I just care about flipping it, right? So we can talk about relations. So now I want to talk about inverse functions, right? So we say that we use this is an inverse relation of a function f if when we compose these, this is equal to the identity. And what identity is it? Well, if F maps from A to B, right, then these two won't be the same. So maybe I'll say that F. So if F goes from A to B, then F inverse would go from B to A as a relation, right? Maybe it's not a function, but it will be a relation. If F comes after F inverse, that means this maps from B to B. So this will be the identity on B. Whereas F inverse after F, when I start with F, I get the identity on A. So I need both of these to be true. So notice it's a subtlety. A lot of people just say, oh, if you compose both ways, you get the same thing back. But you have to be a bit careful here because the sets are different, right? Because if we go from F composed F inverse, it means that we go from B to A and then A to B. So overall, we're going from B to B. Here, we're going from A to A. So to make the identity, we need to make sure this is identity on the correct set, right? If this is a function, because remember, it's not always a function, but if it is a function, we call this the inverse function. Right. So here's a theorem, right? Let F be a function from A to B. And so, by the way, one thing I want to note is when I write down the function little f, right, f is always a function. F inverse is a relation. It might not always be a function, like we said before, right? So be careful how you look at that. But this f is always a function. But I'll just say this to be clear. F is bijective if and only if the relation F inverse is a function. Right? In other words, we have bijection if and only if the inverse exists as a function. Right? So why do we say this? Well, look at this guy, right? This is not a bijection. If we want to form the proper inverse, what does the inverse relation look like? The inverse relation actually looks like this. And that's not a function. It fails the vertical line test. But wait, remember that we just did this where we turned this into a bijection. How do we turn it into a bijection? We removed these parts of it, right? But if I remove those parts of it, now I have to remove this thing. But wait, look what we have here. Now that it's a bijection, its inverse relation, that's also a function on the same domain and codomain. So that's perfectly fine, right? So I won't prove this theorem. If you want to, it's not actually too hard to prove this on your own, right? Using the definitions that we've given so far. If you find that you have problems proving that, let me know. We can certainly talk about it. But this is something very crucial about whether or not this thing is a function or just a relation, right? So be very careful. You're always able to write down the symbol. As a symbol, this is defined as a relation, right? It can happen to also be a function, but not always. And so we can't just always call F inverse the inverse function. It's an inverse relation. Because the relation, as we said before, the relation always exists. Whether or not it's a function is a different story, right? Because I can always make this a subset of the B cross A just by writing it down, and that's fine. Because there's no other conditions of being a relation except for being a subset of the Cartesian product. But whether or not it's a function, that's when I'm adding extra things to it, right? So be very careful in how you write these. If you write down F inverse, you're not saying it's a function, you're just saying that, okay, this is the inverse relation such that this is true, which is totally fine. Whether or not it's a function, that's when you have to do a bit more. Okay? So that's really all I have to say about functions. But now I kind of hinted at, well, let's talk about comparing the cardinalities of sets, right? And whether or not there's different types of infinity. Well, that sounds weird to say, but this is kind of the first big thing in mathematics that you will learn in a class like nature proofs, right? Is how we talk about different types of infinity. What does it even mean to talk about different types of infinity, right? So this would be section 3.3 about cardinalities of infinite sets. Okay. So let's start with this. Let's start with just talking about cardinalities, right? So far, we've already said that if I have a bijective function, then these are equal. And we can almost think about, continuing that onto infinite sets. So the first question I would ask is, are there as many negative integers as positive integers? And the answer is obviously yes, right? You can map every single positive integer to every single negative integer, and this works back and forth, right? So obviously there's just as many of them as on the other hand, right? So there's no issues there. However, I'll ask you a different question. What about all integers versus even integers, right? Now this becomes weird because some people say, oh, well, there's obviously twice as many regular positive integers, or rather just integers in general, there's twice as many integers as there are even integers, because we talked about how we had a box, right? And we partitioned this box exactly into two parts, even and odd, right? And so it seems like there's only half as many evens as integers, but that's not true. It turns out they're the same. Why is that? Well, let's write all the integers here. And then here's the even integers, maybe, right? Because if I keep going, I can get all the even integers, right? Well, if I'm going from here to here, I can almost say that f of x equals 2x. We've already shown that this guy is bijective on the reals. So if we limit to just a subset of the reals, the integers, that's also going to be bijective. So it seems that because we have a bijection, the cardinality should be equal, right? And this almost seems to not make sense, right? When we talk about there being just as many even integers as there are integers, right? And so the reason for this is because infinity is weird. We can't just talk about, oh, there's just as infinitely many things in here than there are in here. That it starts being hard to talk about that, right? Now, what we do is maybe we can show that there's just as many of those, right? But maybe that doesn't make sense. But let's look at something that we can conclusively prove, right? I want to compare natural numbers and the real numbers, right? So far, if I just show you a bunch of things, all of whose cardinalities are the same, well, I'm not going to get into it, right? Maybe before I even do this, it looks like maybe something weird happens if it's just a discrete value, right? If I have numbers that I can list out like naturals or integers, then something goes wrong. But maybe what about in the real numbers? Well, let's look at that, right? This is a set, and this is a set, right? When I compare their cardinalities, it's very tempting to say that this is the cardinality of 1, and this is the cardinality of infinity because of the length of the set interval. But remember, cardinality is the number of things in the set. And this is defined as a set of all values between 0 and 1. There's still an infinite number of them, so don't make that mistake. But if we want to compare this, what does it mean? It means I want a function from 0 to infinity to maybe 0 to 1, right? Well, let's draw this out. Here's one way to do it. Here's my 0 to infinity, right? So maybe my x value is somewhere in here. And I want to map it to an f of x. So maybe this is 0 to 1, right? Let's pick an f of x somewhere in here. How do I get that? Well, what I'm going to do is I'm going to have this point at -1, 1, right? So in other words, what I'm going to do is if I pick an x, I'm going to draw a line down to the x. And wherever this line crosses the y-axis, it has to cross between 0 and 1 because it started at -1, 1. We'll call this f of x. How do we define this function? Well, we've got triangles, right? The ratio of this to this must be the same as the ratio from this to this. So let's look at the first ratio. I've got f of x over x, over this over this. That has to be the same as this divided by this. But what's that? The height is just 1, right? I fixed it at 1. What about the bottom? This is x, and this is 1. So that's just x plus 1. So f of x would just be x over x plus 1. And it turns out you can show that that function is bijective, right? Because what's the only, well, first of all, the obvious thing you might say is, well, what if x is equal to -1? That doesn't exist. Well, look, we're only defining our x from 0 to infinity, and this has a codomain of 0 to 1. And it turns out you can show this is bijective, and that's a good exercise for you guys. Show that it's injective, show that it's surjective, but that won't be too hard, right? You can show that if f of x equals f of y, you just plug in x and plug in y, you end up getting that, okay, x over x plus 1 is equal y over y plus 1. Can you show that that means x equals to y? Well, it turns out you can because x is positive. Same thing, if I give you something from 0 to 1, can you provide an x where it's equal to x over x plus 1? You also can, right? You can easily solve it actually, right? Treat that as just an algebra problem. It becomes just a quadratic formula. And in fact, not even a quadratic formula. It's just a linear problem. So this is bijective, which means these cardinalities are the same, right? I've got two very different infinite sets that are both, continuum in some way, right? But they're the same. So the idea is, if there really are different types of infinity, I can't go ahead and keep showing you these things where they're equal. I have to be able to show you, two sets whose cardinalities are for sure different. So here's the idea. This is called Cantor's diagonalization argument. There is a formal version of this, but I'm not going to give the formal version, right? It's much easier to see it as a picture. There's multiple definitions to show that. There's multiple ways to show these don't have the same cardinality. This is the easiest way, and I'll just show it kind of as a diagram. It's very, very easy to see the diagram. If I write on the formality, it might be a bit involved and take a bit of time, but it won't provide any extra information, right? I'm not trying to show you guys this is a formal proof. I just want you guys to see why these things don't have the same cardinality. So if I have a function, I can maybe write it like that, where here's my n's and here's my f of n's, right? So this is 1, 2, 3, 4, 5, 6, 7, and so on, right? And so here, I'm going to put this like this. Let f be any function going from n to r. Doesn't matter, just any of them. Just pick one. That means for all of these, there's a real number here, right? Well, let me just come up with some random ones, right? 0.4572, blah, 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 right? 1.3163, blah, 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 and so on. And this keeps going, right? If you wanted to make this proof easier, you could also just make this always zeros by saying that this is n to the set 0, 1, and that also works, but we're just going to stick with real numbers for now. Well, here's the thing. I can do this forever, right? Because I have a function that maps every single natural number to every single to some real numbers. I don't know whether or not it's bijective yet, but I know it maps to real numbers. Some of these might be the same, it doesn't really matter. But here's the trick of the diagonalization, right? We can call this like let's say this is like the first decimal, the second decimal, the third decimal, and so on and so forth, right? Two numbers are only the same if every single decimal agrees, right? So what I'm going to do is I'm going to construct a new number. Construct x using the following, right? The first decimal, for each nth decimal of x, right? If the nth decimal of f of n is not 0, then make this 0. And by this, I mean the nth decimal of x, right? If this is 0, then make this 1, right? So in other words, what does this mean? Well, let's look at the first decimal of f of n. Is this. And then like this, like this, like this, and then maybe if I have another value, right? 4.321004, blah, blah, blah. Well, now this is 0. So for example, this value, this x would start with 0.00001 and so on and so forth. Right? This will keep going. But notice that what I constructed will always be a real number, even if I keep going forever. But this would never show up in here. Because just by the way I constructed it, I said that you pick that nth decimal, as long as I make this not equal, there's never going to be one that matches up. Right? And so that means what? That means this is not surjective. I found a real number that will not get mapped to. So this construction uses that I pick any function f, no function of f from n to r is surjective. So that means these are not bijective. And what does this mean? Well, if it's not surjective, then I've got a problem. They're not equal. Right? So what this tells us is the cardinality of n is not equal to the cardinality of r, the real numbers. Right? So that's a big problem, right? We need to find a way to fix that. Well, not necessarily fix it, but we want a way to talk about cardinalities being infinite, right? So this is why we're going to use that, right? We're going to use these ideas. So here, these weren't definitions. We just got these from properties of finite sets by the pigeonhole principle. And so if we want to extend to the infinite case, we can use a definition in the infinite case to talk about this, right? So let x and y be infinite sets, right? Then if x is less than or equal to y, or rather, if f mapping from x to y is an injection, or is injective, then x less than or equal to y. Right? I can write this differently. If x is less than or equal to y, that means there exists an f which is objective such that f maps from x to y. Right? So the idea is being able to compare cardinalities in some way tells us whether or not an injection exists, and so on and so forth. Right? But really, what this says is this statement. If f is injective, then x is less than or equal to y. That's the key takeaway. That's a key takeaway. Right? And so I can say the same thing for surjective. And so that brings us to our final thing, bijectivity. And we'll write this a bit more formally. If there exists f of an x, a function mapping from x to y, such that f is bijective, then we say x equals. So this is the definition. We define the cardinalities of infinite sets to be equal only if there exists a bijective function between them, right? Doesn't have to be all of them, right? Just one of them. So for example, I can construct a non-bijective function between, say, the integers and the even integers, which are called 2, right? And we'll see this notation a bit more in the algebra section next week. But for now, we've shown that there does exist a bijection. If you take f of x equals 2x, it's bijective. This is still a function, right? It's still a function mapping the integers to integers, But now this is no longer surjective because if I take an odd hit, hold on. No, that is surjective, but it's not going to be well defined because, for example, if I put in odd integers here, I get back something that's not in my code already, right? So that doesn't work. So the idea being that it doesn't have to be that every single function between them is bijective. That's not what it means, right? It means that as long as there exists one such that works, then I have the property that I need, right? That's a weird thing about infinite sets. A lot of ways you can map them, but if there exists one that's bijective, then that means my cardinalities are the same. So using that definition, I'm going to define two terms that are usually defined in very, very different ways, right? So not first, I'm going to give my definition, and then I'll give the standard definition so that you can see what the similarity is. You say a set A is countably infinite. That was terrible. So it's countably infinite if cardinality A is equal to cardinality M. This is not the standard definition, but it works perfectly as a definition, right? I'll give you the standard definition. So I'll say this is my definition that you guys are one or more confused, right? And it's correct. But the standard definition is that the set A is countably infinite if there is a bijection or there exists a bijection F from the natural numbers to A. Right? In other words, usually you would want to construct some function where you start at the natural numbers and you get to this set and you somehow show that this is a bijection, right? That's what it means to be countably infinite. But really, since I've defined what it means for cardinalities to be the same, we can exactly use this notation, right? So notice I said countably infinite. This is something that not many people use very well. I was even under an incorrect impression until a couple months ago. So I'll give this definition for now. We say that the set is countable if it is finite or countably infinite. So the idea being you can count it, right? If it's countably infinite, I can still sort of count it using the natural numbers, 1, 2, 3, all the way up to infinity, but there's still a way to count. If it's finite, I can also count. I just stop somewhere. That's the idea. A set is called uncountable. Sometimes you hear uncountably infinite, but uncountable itself already implies infinite, right? If it is neither countable, sorry, if it is not countable, right? So if it's neither finite nor countably infinite, we'll just say not countable. That's how we're going to define it. And I'm not going to claim by proof that every set is either countable or uncountable. That's actually an axiom. Some people like there's this weird thing called the continuum hypothesis, and the whole idea is we have to axiomatize whether or not there is a set whose cardinality is between the naturals and the reals, right? So we kind of saw that the cardinality of the naturals is not the same as the cardinality of the reals, right? But there's been a big question in set theory and logic talking about, okay, what if there's something in between, right? That's something that's more up to the axioms. Then it gets very, very complicated. For you guys, we'll just keep it as uncountable and countable. And unless you ever go into logic and topos theory or type theory or set theory, like very deep set theory, you basically only have countable and uncountable. So that's totally fine for now, right? So the idea is we have countable sets and uncountable sets. Now, most of the time, when someone says a set is countable, they're referring to an infinite set, right? But technically, by definition, countable refers to both finite and infinite sets that are just countable in some way, right? It gets very confusing. I used to think that the term countable only refers to countable infinite, right? Because some books would say, oh, prove this thing is at most countable, right? Meaning prove it's not uncountable. Well, if it says at most countable, why not just say countable, right? And it's just really bad notation. I think some books or some people will refer to countable as usually just infinite sets, right? And finite sets are separate from countable sets. So some people will say you have finite, countable, uncountable. Some other people will say it's countable and uncountable, right? So personally, I use countable, and when I say countable, I usually mean an infinite set, and I usually stick with that. But technically, by most definitions that I found, countably infinite and countable are technically different. So we'll go with this definition for now. But for your sakes, colloquially, if you hear people talk about countable sets, they're not going to be talking about finite sets. They're going to be talking about infinite sets. So let's look at examples. Maybe I should. Yeah, let's do this. We don't need this anymore because we have our proper definitions. It's more of an existential definitions, right? So, examples of countable sets. Well, obviously, every set has the same cardinality as itself, reflexively, right? So N is countable. It's the most obvious countable set that we have. Now, what about the integers? Right? So the idea here is let's see why the integers are countable. Well, what I can do is list all the integers, right? But if I list them in a normal way, I won't be able to count them because I'm going to infinity in two different directions. That's not fine with counting, right? But what if I just started from 0 and did this? 0, -1, 1, -2, 2, -3, 3. Now I'm only going to go to infinity in one direction. And I can count this. If I really wanted to, and maybe you can do this as an exercise, you can try to see what this function is, right? If this is 1, 2, 3, 4, 5, you can figure out what this function is, right? And show that it's bijective. And the idea is you will be able to, right? This will be a bijective function. I'll always be able to map every single one. Every single integer maps back here. That's surjective. And if I have two different, well, I'm not going to get two different numbers anyway, right? I'm making these all unique. So this is going to be bijective. What about the Cartesian product of the naturals? Well, that's also countable, right? So the idea is when you're taking the Cartesian product, right? I have maybe 1, 2, 3, 4 here, and so on. 1, 2, 3, 4, right? These become ordered pairs, and so on, right? Well, the idea is I can count these diagonally, right? I start here, I go here, I go here, I start here, go like this, and I keep counting diagonally. Now again, even though this is like 3 different directions almost that I go to infinitely, when I count this using the orange direction, right? Now there's only one way in which I'm going to infinity, right? And now this I can count as well. So this is another way to show this is countable. Obviously, the diagram I'm showing you is not a formal proof, and generally you don't need a formal proof to show something countable. It's kind of taken for granted, but you can sort of see why. If you really wanted to, you could come up with a formal definition for this, right? And that's fine. Here's one more quick example. The rationals. The rationals are countable, right? And so, well, if I just take this with the positive rationals. The positive rationals are integers, positive integer a over positive integer b. I can say that, right? So again, these are just integers, right? Same thing as n cross n. But some of them just won't be the same, right? For example, 1 over 1 is the same as 2 over 2, right? So the idea is just do the same counting, but just skip over the ones you've already included. And that's still going to be infinite in the same way, right? Now notice I just did the positive rationals. I claim that the union of countable sets is countable. And why is that? Well, it's the same reason for the integers, right? I can kind of pick one from each union, right? So for example, if I take the union of, so let's say that A and B are countable, and I look at A union B, I want to count it in some way. Well, what if I just did A1, B1, A2, B2, A3, B3, and so on? That's countable, right? So I get A union B is countable. Well, what if I did union C? Well, this is induction, right? Essentially, the idea is even if I have an infinite union of countable sets, this guy's countable. So base case, the first guy's countable, you're done in the n equals 1 case. What's the inductive hypothesis, right? If I have A1 union A2 all the way to AK, right? I want to show that the union all the way up to AK plus 1 is countable. Well, what is the inductive hypothesis? It's that this guy's countable. Well, if I add another one, that's the union of two countable sets. So call this A and call this B, you have the same idea, right? So the arbitrary union, if I just take any union of countable sets, it's countable, right? And rather, I should say the countable union of countable sets, right? I can't take an uncountable union of countable sets. That doesn't make, that's obviously not going to be countable, right? But if I take a countable union of countable sets, that's going to be countable. So the rationals are really just the positive rationals, union 0, union the negative rationals, which will be countable for the same reason. So the rationals are a union of 3 countable sets, and thus it's also countable, right? There you go. So unions are countable. You have examples of sets which are countable. But essentially, if I gave you a set and I wanted you to show that it's countable, you essentially want to show that, by definition, you want to show that it's the same cardinality of the natural numbers, or in other words, your job is to construct a bijection, right? That's the idea of showing that something is countable. And so, if it's uncountable, then we claim that it's going to have the same cardinality as R, right? So examples of uncountable are, right? Now, what about the irrational numbers, right? So consider the set of irrational numbers. This is a good proof by contradiction, right? The idea being that, well, maybe I can't show exactly that there's just as many irrational as real numbers. It's harder to show. But take this: the real numbers are partitioned into a union of irrational and rational. Well, we already know Q is rational. So let's call this set, like, I don't know, let's call this set T, right? Let's say T is the set of all irrational numbers. Suppose T is countable, right? Then note that R is a union of T and the rationals, right? R is a union of irrationals and rationals. But if T is countable, then this is a union of two countable sets, which we said is countable. So this implies that R is countable, which implies that the cardinality of R is equal to the cardinality of natural numbers, which we've already said is false, right? We've shown that these aren't the same, but this is a contradiction. So our assumption must be wrong, and so T must be uncountable. So this is the easiest way to show that the irrational numbers are uncountable, right? And this is a standard technique to show that a subset is irrational, is usually to show that, okay, if the overarching set is, to show that a subset is uncountable, well, you essentially want to use the fact that the overarching set is also uncountable, right? You can't have an uncountable set inside a countable set. I mean, that's just too much, right? So if your overarching set is uncountable, to show a subset is uncountable, maybe take its complement, right? Take the opposite. If that's countable, then you're done. Because if you take out a countable set, you're still left with uncountable things. That's the idea, right? It's sort of the reason why you can't take infinity minus infinity. It depends on the type of infinity, right? Countable set minus the countable set, it could be 0, it could be infinite, right? If I take the set of natural numbers, subtract off or remove the set of natural numbers, I get the empty set, cardinality 0. But if I take the integers and remove the even integers, it's still countable minus countable, but I'm left with countable, right? Because the number of odd integers is still countable. So you have to be very careful. You can't subtract infinities. We have to look at it this way, right? We have to kind of prove it based on something we know about these sets, right? One last thing, there's a theorem by Cantor, Bernstein, and Schoenberger, I think. I don't quite remember who was it. There's three guys. One Cantor was one of them. Essentially, it says that if if there exists an injection F from A to B and from B to A, right? So if there exists F from A to B and G to B to A, such that F and G are injective or injections, then there exists a bijection H from A to B. In other words, this means that the cardinality is the same. And we can all see this, this is sort of why we had the definition I showed you before, right? If there exists an injection F from A to B, and there exists an injection G from B to A, that means the cardinality of A is less than equal to B, and the cardinality of B is less than equal to cardinality of A. But here's the problem. Beforehand, when we were dealing with finite numbers, we could put these two together to say they're equal, right? But now that these are infinite, we can't quite say that. Just because this is less than this and this is less than this doesn't mean that they're equal. Infinities can be not equal, right? So that's why we have this guy, right? This theorem tells us that, well, if this is true and this is true, we can show that there exists a bijection. But by definition, because there's a bijection, we then get that their cardinalities are equal, right? So that's the idea. So that's why this theorem doesn't show up a lot. It's just kind of I provide this, and it's usually an important introductory theorem in a lot of these books that show this sort of countability and uncountability introductory ideas. Is basically just to show that even in an infinite case, we have a way of turning this into this. We just can't do it in the normal sense that we do in the finite case, right? Because infinities are weird. So this whole part of the lecture, this whole last 40 minutes, was essentially my way of saying infinity is really weird. You can't add or subtract them as you usually do, but we can still talk about them in terms of sizes of sets. If you want to compare the cardinalities of the sizes of sets, there are arguments with which you can do it, and that relies on comparing them to the natural numbers. So with that, this essentially concludes the first part of the course, which was the introduction into what would be covered in an intro to proofs class, right? So the way, for those of you who might be watching this in the future, who might be in the US, I don't know how it's done in other countries, but typically in universities in the US, you're done with like Calc 1, Calc 2, Calc 3, you maybe take a linear algebra course before or after this, but the first introduction to proper math courses is usually called like Introduction to Proofs or Introduction to Mathematical Thought. It's some way of introducing you not only to the ideas of proofs, but to the ideas that you'll see throughout the course. Everything that we've done up to now is usually included in a course like this, and I've actually included a bit more material than you normally see. But this, what I've done from lecture 1 up to the end of today is the entirety of what you would expect to know from an intro to proofs class. Right. So for those of you who haven't taken the intro to proofs yet and want to see if you're ready, let me know. I can certainly come up with a test that you like, sort of like a final exam that you would have gotten from the intro to proofs class, right? The reason I'm doing this in this class is because I think section 1 and section 2 go really well together on their own as kind of something to give as a test for what I'm doing in this class. But I also don't want to give like just a test in section 3 by itself with 1 and 2. So what I'll do is I'll eventually give a quiz on section 3 itself, right? So I'll give a quiz on basically relations, functions, countability, that kind of stuff. There'll be the test that I give out sometime this week on sections 1 and 2, right? And then I'll keep going over the rest of the course. But for those of you who want to know whether or not you'll succeed in an actual intro to proofs class, it's all the material from sections 1, 2, and 3. So if you want me to email me and I can come up with a test just on those 3 sections and give that to you, right? Because that will essentially be what you would expect from final examination proofs. So the game plan going forward is we're going to take a break on Friday. So I'll give you all a break on Friday. We won't have class on Friday. I might give some extra practice questions just to fill that time. So we won't be meeting, but I might assign stuff over email. And then on Monday, we're going to start with our topics, right? So for now, I still don't know where or when I'm going to put all these topics, but at the very least, we're going to start with abstract algebra. So this class has many names. Some people say modern algebra, some people call it foundations of algebra, some people call it abstract algebra. It's all really the same thing, so I'm just going to call it algebra. So don't know how many sections I'm going to have. It'll be at least 3. Oh, I'll teach at least 3 sections. So I'll teach the basic material that you would get in an undergrad course, and then I'll start showing you some of the applications as to why it would be important. Algebra is, I risk saying this publicly, but in my opinion, a lot of what's covered in an undergrad class in abstract algebra kind of falls into a dead field of mathematics that isn't really needed anymore, because we've classified a lot of things about algebra. For example, there already exists a classification of all finite simple groups. That's all done. We don't even care about that anymore. But one of the biggest applications of algebra comes from physics, where you talk about things called Lie algebras, and to understand that, you need to know all the fundamentals of algebra itself. So that's one of the things I'll talk about in algebra. From there, we're going to cover row analysis. Some schools will call this advanced calculus, because essentially what row analysis is you would take the things that you've learned in Calc 1, Calc 2, and so on, and you would start learning how to prove that they're true. We start learning how to conclusively prove results that seem really obvious, right? So we'll start talking about things like distances between sets, distances between numbers. We'll talk about a lot of things, like for example, you guys know there's the mean value theorem, the intermediate value theorem, all that stuff. We're going to learn the techniques to prove a lot of stuff like that. These two, this course is more about definitions and understanding definitions. Obviously, there will be things to prove and there will be theorems, but algebra is always a lot more about understanding definitions. Whereas row analysis is more about the actual proofs than the definitions of. There won't be a lot of definitions in row analysis, but it's a lot more proof heavy or theorem heavy, right? So by showing these two first, you'll kind of see the back and forth. You kind of see that there's two very different ways to approach a field from either definitions or theorems. After that, we cover topology, right? So topology can be a mix of both algebra and row analysis. There's a lot of different types of topology. I'll just be covering general point set topology and a little bit of general topology, just to kind of give an introduction to some of that stuff. But I won't go too far into, say, algebraic topology, which is definitely much more of a graduate course in my opinion, right? You can definitely have an undergraduate course in algebraic topology, but it certainly wouldn't go too far. It's definitely something that requires a little bit more mathematical maturity, but it's certainly doable if you're good at, parsing the definitions. There's a few topics I want to do after that, but I haven't decided on the order yet. It just depends on how, as I get back homework and as I get feedback from the course, I'll kind of see how you guys do with these 3, and then based on that, I'll decide what to do next, right? Some other things might include category theory, number theory, graph theory, complex analysis. I have thought about doing differential equations, but I think differential equations at an undergrad and early graduate level is much more of a computation class rather than a proof stage class. So I'm going to leave that out for now. But if you have any questions about those, you're more than welcome to ask me. I can maybe find some ways to relate those to stuff you've already seen. So I know I've talked for a while, so that's where I'm going to end for today. But this is what you should expect coming up starting next Monday. And then after that, we will go into just, we'll look at different types of problems that you'll say. You will talk about different types of mathematics you will be within each of these fields. And that'll at least give you a good introduction as to what to expect throughout, a math degree, for those of you who haven't done one yet. And for those of you who have a math degree and are going into graduate school, these will give you a sense of like, okay, what should we actually do in building up these topics? How should we kind of see these topics related to each other? And so I will see you guys on Monday then.